Nancy ma'am,
Yeah, ma'am.
if participant does not mute your audio, kindly give exit, ma'am.
Okay. Okay. I'll do that.
A very warm good evening to all dignitaries, guests, and delegates. With great joy and immense pleasure, I, Dr. Ajay Karthik, Associate Professor from the Department of Computer Science, Savitha College of Liberal Arts and Sciences, feel privileged to extend our warm welcome to you all. Join here for the 5 days International Online Faculty Development Program series on advanced techniques in computing sciences and applications. Let's start the program by remembering our God with a prayer. Lord, we pray for the every living creature and give us strength to endure and rebuild. Dadbrushahi vidmage vagradundaya dhimahi danno dandi prashodayat. Savitha Institute of Medical and Technical Sciences (SIMATS) was established in 2005. We are very proud to share you all that our SIMATS has been re-aggregated by NAC as A++ grade with a score 3.6. SIMATS ranked with many more ranks. To mention a few, SIMATS ranked A++ grade by Our World Institutional Ranking for the Outcome-Based Education Ranking 2022. Tamil Nadu government has given approval to 6 universities, including Savitha, to start a greenfield university. Savitha College of Liberal Arts and Sciences, ranked with the Indian Institutional Ranking Framework, has conferred with 19th national rank and 7th state rank in the University Ranking in India 2022 for Arts and Science team. Savitha College of Liberal Arts and Science to emerge as a preeminent college by importing excellence in education of global standards with research culture and creating the individuals with ethical values to serve the society. We have offered the program BSc Computer Science, Computer Applications, Artificial Intelligence, and Data Sciences. We have well-trained the known CBCS system, which provides an opportunity for the students to choose the courses from the core, elective, and skill-based courses and foreign languages courses too. The students are offered study abroad program with the Asia Pacific University, Malaysia, and completed their international workshop and credit course on artificial intelligence and data analytics. It will be prolonged with various courses offered by the US and UK universities too. Students trained in the hands-on coding, implementation of research projects, and comprehensive training for every subjects they have studied. On behalf of Department of Computer Science and Application, Savitha College of Liberal Arts and Sciences, we extend our profound gratitude towards our respected Chancellor of SIMATS, Dr. N.M. Veerayan Sir, respected Director Academics, Dr. Deepak Sir, Dynamic Director, Madam Dr. Ramya Deepak, and Vice Chancellor, Dr. Sandaram Sivaji Sir. We wish to express our heartfelt gratitude to our Principal, Madam Dr. Punita Arun Chandok, who gives direction to every student and faculty members. This is an occasion we get opportunities to test our knowledge and understanding. It is a moment of knowledge speaks but wisdom listens. I am glad to invite Dr. A. Henry Juliet, Associate Professor, Department of Computer Application, to introduce our chief guest of the day.
Thank you, ma'am. Am I audible, ma'am? Good day to everyone. Your work speaks volume of the kind of man you are: efficient, organized, and result-oriented. It's a pleasure to work with someone who knows how to make a friendly and inspiring work environment. I thank the management, director, principal, faculty members, and participants for this wonderful opportunity. Thank you all. If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. Words of John Quincy Adams. A man who exactly matches for these words is our chief guest. Yes, it's a great privilege and honor to introduce our chief guest, Dr. Houssain Kettani, a professor in the Department of Computer Science at Akhawayn University in Ifrane, Morocco. Dr. Houssain Kettani received the bachelor degree in Electrical and Electronic Engineering from Eastern Mediterranean University Cyprus, and master's and doctorate degrees both in electrical engineering from the University of Wisconsin. Madison, Dr. Kettani has over 20 years of academic experience. He served as faculty member at the University of South Alabama, Jackson State University, Florida Polytechnic University, Dakota State University, and University of South Carolina, Aiken. Dr. Kettani also has served as staff research assistant at Los Alamos National Laboratory, visiting research professor at Oak Ridge National Laboratory, visiting research professor at the Arctic Region Supercomputing Center at the University of Alaska, and visiting professor at the Joint Institute for Computational Sciences at the University of Tennessee. Dr. Kettani's current research interests include cybersecurity and data analytics. He presented his research in over 100 refereed conferences and journal publications, and according to Google Scholar, his work received close to 1,000 citations by researchers all over the world. He carried over 100 international conferences throughout the world and successfully secured external funding in millions of dollars for research and education from US federal agencies such as NSF, DOE, DOD, and NRC. Sir, we are feeling pleasure to have such an eminent speaker as today's resource person. Thank you.
Thank you, Dr. Hensi, ma'am. Now, without further delay, we will turn the time over to the eminent speaker. Sir, please, now the time is yours.
Thank you very much. I'll just share my slide. Thank you very much, Dr. Hensi, for the introduction. Thank you very much, everybody, for your attendance. I'm glad to be back to Chennai. Do you see my slides?
Yes, sir.
Okay, great. Thank you, Savitha College of Liberal Arts and Science for the invitation. I'm very pleased to be the first invited speaker at the International Online Faculty Development Program on Advanced Techniques in Computing Sciences and Applications. I'm very glad to be back to Chennai, although it's online. I hope at some time I'll be able to come back physically when things permit. Today, a very related topic to this conference. I'll be talking about advances in high-performance computing. So in algorithms, the first one of the first equations that undergraduate students see is this equation, which basically relates time to capital C is the basic operation count in an algorithm, and little c is how much time it takes to execute that basic operation like multiplication or addition. And with that, so little c depends on technology, capital C depends on the algorithm itself. So so analysis of algorithms talks about capital C, and because and that makes the analysis of algorithms independent of technology. So so that way we can compare different algorithms that were produced or analyzed like from 2,000 years ago with a new one that is produced now, because of course technology becomes faster and things improve, so it doesn't make sense to compare the time of different algorithms on different technologies, but we compare algorithms themselves with the number of basic operations. So in how algorithms perform in terms of efficiency. So when we consider C of n, if it's log of n, it's good. N, we call it linear. N log n is good. N squared, it's quadratic. N cubed is polynomial. So n to something, we call it polynomial. N to 3 is cubic. And then, so these are all like kind of good algorithms. But then you have exponential and you have factorial. Like you have a knapsack problem, like the brute force algorithm for knapsack problem. We have traveling salesman problem. So these, as you can see, for little n, if n is 100, then this is 10 to 30 or octillion, and this is 10 with 1 with 156 zeros or 158 zeros almost. And then if it's 1,000, so this is like it's very hard to come up with this number. And then you multiply this number with how much it takes a basic operation to calculate, and then you get centuries or more. So we're going to get back to this algorithm to see how, even with current technology, how can we, how such algorithm does. Of course, the whole analysis of algorithms tries to improve an algorithm so it doesn't fall in these categories like exponential and logarithm and the factorial, but sometimes especially if you need to combinatorial problems and combinatorial optimization problems in which you want to find, you want to see each instant and find the minimum or the maximum or something similar to this, then you run into the issue of exponential and factorial no matter what you do. So, so the basis of parallel computing is that you have a number, a size, an input size. Say if you have an array of 1,000 elements and you want to find the maximum, so you can send the first 100 elements to a processor and then the others. So use 10 processors, each one you send it 100 elements, and then you find the maximum of each sub array, and then the maximum of these maxima gets you the maximum of the original array. And this is the basis of Arabic parallel computing, which also referred to as divide and conquer algorithm design strategy. So here is the fastest computer in the world at Oak Ridge National Lab, where I worked for several summers, and it's called Frontier. So this is what it looks from the front. From the back, it would look like this one. The room is very cold. It's raised by about 1 meter and chilled, and it's cold, humidity controlled, so that the system works well. And it costs millions of dollars for just its electric energy, and then other millions for maintaining it, through staff and personnel and equipment and other things. And so it performs 1.7 exaflop per second. It is the fastest. There is a list that of the top 500 computers, top fastest 500 computers in the world, and the list is updated in June and November, and it just updated this month. And so this in 2022 we just reached the exaflop, which was exaflop mark, which was a big news. So this current computer performs a quintillion calculation per second, or 1 with 18 zeros next to it. And so in comparison, in 1985, we hit gigaflop ceiling, or a billion calculation per second. And in 1997, we hit the teraflop ceiling. That was the fastest computer in the world. In 2008, the petaflop, or 10 to 15. And in this year, we just reached 10 to 18. So now your smartphones in your pockets are faster than the fastest computer in the world that was in the 80s. And that cost millions of dollars to operate and was hosted in an acre, a room that is the size of surface area of acre. And it cost millions of dollars to operate and had several personnel with it. But now all that you have it in your pocket, just to see the progress of technologies and the progress of human advances in science and computing science and its applications. So by extrapolating such advances, by 2030s, we will reach the zeta flop, and that would be 1 with 21 zeros next to it. And then you have the Utah scale by the end of 2040s, or 10 to 24 calculation per second. And after the Utah, there is no word for that. So 10 to 27, there is no word in English. So the language is trying to catch up with the speed of these computing devices. So this one consumes, Frontier consumes 21 megawatt, and that's more than consumption of a whole university, of a typical university campus. So implications: exascale computer has processing power on the order of processing power of the human brain at the neural level. Excellent resource for machine learning, for data analytics, artificial intelligence, and also for cybersecurity. There is also talk about quantum computer, and for specific application, it's trillion times faster than the fastest computer, it performs 10 to 30 calculations per second. So there isn't a word for that. Google, one example is Google Sycamore quantum processor. And so there is a saying that the country that outcompetes, because developing such fast machine helps in industry, helps in national security, helps in science, technology, cybersecurity, national security, and critical infrastructure of countries in general. This is historical. So the historical fastest computer in the world. So the orange one is the fastest computer in the world. You can see that it reaches steps and then it remains there. So each triangle is 6 months period. So here, like a year and a half, one remained there as the fastest. And so you can see step. You can see a lot of competition trying to find a better technology, and then there is a breakthrough. There is establishment of a much faster machine, and then this one remained there for 2.5 years, and then you keep going until we are here. So here we just reached the exaflop, and in 2022. And so if you do the extrapolation like that, the linear extrapolation, and on this semi-log plot, that's when you get the estimation that about every 12 years we reach to a new scale. Here is the top 10 that just published this week at the Supercomputing Conference. And so the fastest is Frontier. It's in USA, and then the second fastest performs half of that performance, which is in Japan. And the third is in Finland. The fourth is in Italy. The fifth in the US. And then somehow China, Tianhe 2 was the fastest computer in the world, but now it's the 10th fastest computer in the world. So you can see how in this business you have to stay up to date, otherwise you keep going down and down in the ranking. The fastest computer in the world in Africa is in Morocco and entered the top 500 in 2019. It ranked 130 in 2021, but 162 in 2022, and it performs 3 petaflop per second. So the Frontier performs more than 1,000 petaflop per second. So this is about 3% of that performance, or less, 2%. And the name Topkal is the name of the highest summit in Morocco, or the highest summit in North Africa. So let's, for example, let's compare a supercomputer with a typical PC that we use. So a typical PC achieves about 1 teraflop per second, that's million times faster than so the Frontier, the supercomputer, is million times faster than a desktop. And so 1 second in a supercomputer perform is more than 12 days in a PC. 1 hour is more than a century. So what does that mean? It means that problems that were not solvable before because you cannot wait a whole century now are solvable. So things that took centuries now take few hours, and that's amazing and shows how we can analyze things in much better granularity and faster and more accurate. So weather forecast or analysis of hurricane track becomes much more accurate. Analysis of surface of cars or friction with wind becomes much more smoother, much more better. You can analyze it in much smaller granularity, like these pieces of the surface can get smaller because you can fit more data, and your analysis you don't have to wait much longer. So quantum computer, if there's a functioning quantum computer that is stable, then it performs 1 trillion times faster than a supercomputer. And so 1 second in a quantum computer would be more than 30,000 years in a supercomputer. And then even so, it would be more than 1 billion years in a PC. So it's still a work in progress when we talk about quantum computing. And there are some like the Sycamore computer that is produced by Google. It's problem specific, so there isn't some working quantum computer that we can have in a stable one that we can have in our in a lab or something. So how slow is it anyway? So for example, if we have a problem that is exponential 2 to n, like a knapsack problem, if we have n is 100, then that is about 10 to 30. So suppose we have this 1 exaflop supercomputer at our hand, and we dedicate all its performance to solve this problem with input size of 100. Then the time that a basic operation is performed will take 10 to minus 18. So if we plug it into the equation that we started the presentation with, we get about trillion second, and that's about 32,000 years. So this is a supercomputer. This size of a problem will take 32,000 years, which makes it not solvable. So with a quantum computer, we can solve it in 1 second. So that's why there's so much talk about quantum computers, and there's so much excitement about quantum computers. On a typical PC, it's gonna take billions of years, and of course, in both supercomputer and a PC, it's not solvable because nobody can wait this. It's practically plus infinity. So these problems are so no matter what. So that human ingenuity happens that you improve the algorithm rather than spending so much time in upgrading machines. Of course, in this case, unless you have a functioning quantum computer. But even then, if you have 1,000 elements, then this becomes slower. So, for example, knapsack problem, brute force exhaustive search is exponential. But if you apply a dynamic programming algorithm, then it becomes linear. So with that particular problem, the problem solved. But still, with current supercomputer at Oak Ridge National Lab, there are some problems that it takes months to solve with supercomputers. So there are problems that we were not smart enough to reduce them from exponential to polynomial. If we are talking about cracking, like for example, advanced encryption standard, which is a widely used encryption algorithm, if we apply current technology or Frontier 1 exaflop supercomputer to crack it, if we do the math, it's going to take 10,000 years, it's going to take 10 to 16 or 10 quadrillion years. So it's impossible to solve this with a combination of all keys. With the quantum computer, it's going to take 10,000 years. But understanding that each 12 years, our quantum computer, our supercomputer is going from, is becoming 1,000 times faster. So if we extrapolate, we can see that by 2090, it will take few days to crack advanced encryption standard with a key that is 128 bits. Of course, excluding the possibility of quantum computing, which could be a trillion times faster, which makes it much earlier, like maybe in mid-century, if there's a functioning quantum computer. So let's talk about hardware versus software and limits on speed and physical limitations. So in the past, there's Moore's law that says that the speed of computers double every 18 months. And the problem with the heating is like running. When you are running, you produce heat. And so when you are, when you are with the speed of computers, the processor heats up. And then it's warmed up to a point that it melts or malfunctions. So we couldn't keep increasing the speed of one processor. So a solution to that, a hardware solution to that, was to put two processors and call it dual, or four processors and call it quad. So each processor would be 1 giga, and then if you put 4, you set it as 4 gigahertz, but quad. But so hardware engineers solved the problem, and they didn't really solve the problem. They just hit the can, passed the ball to software engineers. So software engineers face the following problem: is that if you have 4 processors, if your software or program or operating system operates in serial, then it's going to just use the maximum of one processor because it cannot use several processors at the same time. So they worked hard to make their software and programs work in parallel to maximize the efficiency or the use of all processing power of a machine, and that took several years. Now the question comes: is that every serial problem can be solved in parallel? And so, for example, if you try to build a high building, you cannot start from the top or the middle because of gravity. You may build it in blocks and then assemble them like a Lego. So that's the closest you can get to parallel solution to such a problem. If you are building a bridge, similarly. Another example that is classically mentioned in this serial to parallel paradigm or limitation is pregnancy. Can you get like 9 ladies 1 month each and then you get a baby? And the answer that we know so far is no, that's not possible. So it's a counter example that is mentioned in the literature that not every problem can be solved in parallel. So by way of a proof of concept, so if we talk about number representation, so you have if we are converting a decimal number to binary, then and it happens with any number system, binary, ternary, base 4, base 5, etc. Then the way how we learned it is that you do repeated division to produce the integer and repeated multiplication to produce the fraction part. So and then to calculate this, it's just a weighted sum to get back to your decimal value. And so here's an example of repeated division. So for binaries, so you get the remainder. So 41 in decimal is this 101001 in binary. And this is because I divided the most, so this becomes the most significant bit. This divides the least, so becomes the least significant bit. Similarly, with the conversion of the fraction part, I keep multiplying and I get integer part, and that fraction in decimal equals this fraction in binary. So what we've done here is we've done it with, if I tell you what is the 100th bit, you need to keep dividing, running the processor until you reach the 100th bit. You cannot tell me the 100th bit directly. But with this theorem that I proved before, it just asks, you already gave me 3 values. You told me the decimal value, which is D. Here it is. You told me the bit position, say 100, which is J. And you told me the base I'm converting to, which is binary. So letter B is 2. So I plug it in here. I get the value of the bit in the 100th position. And knowing that each bit I can produce it like this independently. So a bunch of bits I can produce them independently. So I can produce a parallel algorithm to solve base conversion. So I send a bunch of these bits to this processor, a bunch of these to this processor, etc. And then when you gather all of them, you just juxtapose them next to or concatenate them, and you get the original conversion. And that ends my talk. And thank you very much, and I'm open to your questions. I don't know if you want to pass them as audio or you want to pass them as written, if there are any.
Hello.
Hi.
Hello. Hi, sir. Sir, I have one clarification. Currently, can you give some live example how this parallel computing at present in AI, how it works? Can you give one live example of the current project in AI or DI?
I gave the example of converting on base conversion. I gave an example if, say, if you have an array like a vector and you want to find the maximum number in such a vector. And so instead of running an algorithm that compares each 2 elements and then find the largest among 2, you can write a faster one that sends like the first 1,000 to a processor, another 1,000 to another processor, and you maximize each sub. You find the maximum in each sub array, and then the maximum of the maximum are going to get you the maximum of the whole one. So these are just examples of taking a problem from serial to parallel and how to use parallel computing. So it's like delegating a job to 20 people and tell each one you give them a job, and then the solution, and then the problem is solved by combining the work of all these 20 people, for example.
Thank you, sir. Thank you. Thank you.
Thank you, Doctor.
Hello, sir. Is it audible? I think so.
Yes.
Yes. Nice presentation, sir. Can you explain more about quantum computing?
Well, it's still work in progress. It's just so in computers we talk about binary numbers where each position is either 0 or 1. In quantum computing, it could be 0 and 1 at the same state, so you can fit more information, so calculation can be faster. But there isn't yet a quantum computer that that functions on all aspects, like a computer does. So you cannot just go to a shop and buy a quantum computer. So it's still research that is ongoing.
Jay Karthik, ma'am. Jay Karthik, ma'am.
Participants, you can ask your queries. Thank you, sir, for sharing your profound knowledge with us. Participants, kindly unmute your video for a screenshot for the photo session.
Thank you. Thank you very much.
Sir, participants, kindly unmute your video for the photo session. Thank you all. Participants, please wait for the feedback link. Thank you, professors. You can mute your video.
Thank you very much, and have a wonderful evening. Take care.
For your sharing your knowledge. Thank you very much for your support, sir.
Thanks, ma'am. Bye-bye.